Hi, welcome to the video, and in this video we will be creating a quantum analog of the classical AND gate. But before that, let me get clear with the basics. So this is the normal truth table for the AND gate that all of us are very well aware of, and something similar follows for the quantum analog of the AND gate, but with the only difference that rather than the input and output be denoted by the scalar value of 0, is denoted by 0 ket and 1 ket, which are nothing but actually vectors of size 2, and we'll get into that later, but know that these are vectors. And a very important distinction of the quantum computation from the classical one is that the quantum computation is reversible. So what it means is that even if I am given the output, I should be able to figure out the input. But if you see here in the classical one, if I just give you these zeros, then how you will determine the uh, inputs? It's not possible to determine the inputs, all right? And that's a big difference. And how you actually get the input from the outputs, we will see the mathematics later. And if you are still curious about the mathematics and everything, you can follow this playlist on my channel where I have talked about the mathematics and all of that stuff. It's a long playlist, almost 14 videos. Okay, so with that said, let's get to the business. So let us now create the quantum circuit for the quantum analog of the AND gate. So you can see Q here denoting the qubit, which is the quantum analog of the classical bit, and here C1 denoting the classical bit. All right, and actually we would need three quantum bits or qubits. So what I will do is I will just use this plus icon here, and I'll just get myself two more qubits. So before we proceed, let us just rename here, and we are creating AND gate. All right. So what I will do first is just prepare the inputs, all right. And initially all these qubits are in the zero ket state, all right. So to change them, I just what I'll do is just drag these two gates, which are nothing but quantum NOT gates, which are the quantum analog of the classical NOT gate, and keep an eye on these graphs that are changing. Okay. So now I'll just separate this visually from the next part that we are about to build using these barriers. And it also has the hardware implementation importance, but for now let's just avoid that. So what I have done here is that I have changed the initial state of 0 0 to 1 1 because of the application of these two gates, alright. And now comes the very important part of the Toffoli gate. So this Toffoli gate is the one that actually works as the quantum analog of the AND gate. So let's get to it, and let me explain you a bit about it. What I'll do is just quickly, so you have just like this. This is what how you denote the Toffoli gate. So these first two qubits are called the control qubits, and the last one, this one, is called the target qubit. So what happens is that if these first two qubits are in the one ket state, then the this qubit it undergoes a bit flip. So what happens is that if initially here the value of this qubit is 0 ket, then after the operation it will be 1 ket, and if it's 1 ket here, then it will be 0 ket. So that's the operation of this Toffoli gate in a nutshell. So as you can see here, we are having 111 in this state with 100% probability, and because this is a very straightforward thing, there is no superposition or anything here. So what you can do is, let me just delete the first one, and of course you don't need this barrier also. So if you see, what happens is that the probability of 100% from this state changes to 100% probability in this state. And note that in Qiskit here, the qubits are read from right to left. So in here 010 state, the rightmost digit actually represents the first qubit. Alright. So you can see we have the state here 0, 1 and 0. Since both of these states are not in the one get, NOT operation is not performed. Alright. And let's see if I just drag one here, and if I also drag one here, you can see it's now jumps to 110 state. Alright. Which is what I told you a minute ago. So that's a simple circuit for AND gate and the quantum version. And if you want to save this circuit, you can just go here, download PNG, right? And if I just do this, see a very nice good circuit is saved for you. And if you want to copy the code, you can just copy it. You can also copy it to clipboard directly here. If you want to change the language, you can move to OpenCasm. So I think that's it for the video, and if you have any doubts, let me know in the comments, and we will explore this environment more as we move to other circuits. Alright, take care. I will see you in the next video.